chemistry is just the interaction of any two atoms, and those two atoms can be in compounds, they can be by themselves, they can be at varying different levels or extents. Right? And that's the same kind of concept that we would come up with individual relationships. You could look at people being married to each other, and that's one type of relationship. Okay? And you could look at the different types of marriages that are possible. If we went a step back away from the institution of marriage and just looked at couples, well, there's varying ranges of what makes a couple. Okay? Did they just start being a couple? Are they close to getting married? Are they engaged? Okay? So we've come up with kind of arbitrary standards for those comparisons in our real world relationships. Chemistry does the same thing. So what we do is look at the interactions between those atoms and we start to classify them according to subcategories of what we see in those relationships. Okay? The ones that you should already be familiar with are the ones that we refer to as bonds. Okay? And when we first talked about it in the case of nomenclature. And in nomenclature, we really just had two interactions, ionic, and then we had covalent. So those were our two categories when it came to nomenclature. How did we know it was an ionic bond? So we could go as far as looking at the hardcore definition, no sharing of electrons. The word that you would look for in an exam would be a transfer of electrons from one atom to another. Okay, but that can be kind of hard to tell. If I just give you two atoms, a random bond, okay, where's the bond in that case? Where's the bond between sodium and chlorine? What I just drew up here, right? To the Na, dash, and the chlorine. Where's the bond? Is the bond over here? How about up here? Over here? Over here? Over here? I know you all aren't asleep because I can see your eyes are open. Our bond is the dash in between. Okay, so the definition that we've used for an ionic bond, no sharing of electrons or a transfer of electrons. When we look at this image of a bond in two atoms, where in that image does it say anything about how the electrons are being shared? Nowhere. So while that definition is true, it's pretty useless as far as us manipulating it. Okay? So the next part that we could move to is, well, maybe you just look at how they share electrons, okay, or how bonding electrons are shared. And there's a term, there's a thing that we can use to rank individual atoms and say, how does it share electrons? What was that term? Electronegativity. So we could look at the difference in electronegativity and come up with arbitrary systems for what's ionic or covalent. Okay, but then to do that, what do you need to know? You need to have all of the electronegativities at hand. And I can tell you right now that is very, very rare will you ever have that information immediately at hand. So far our definition for an ionic bond is completely and utterly useless. Is there a better definition? If we take a look at the bond shown, it was nice enough to do this. We have sodium, which is what? How do you know it's a metal? Where it is in the periodic table, which I ultimately told you. Okay, if remember, we look at the periodic table, you see the darkened, bold line jagging at that angle, okay, on the right-hand side. Can we restart? On the right-hand side, everything to the left of that is a metal. Everything to the right of that, non-metal. Anything on that line, we now run to that gray area where it's somewhere in between. Some of those elements we refer to as semi-metals or metalloids. Okay? So where is sodium? The extreme left side of that periodic table, which means it's a metal. Where's chlorine? the extreme right-hand side of the periodic table, which means it is nonmetal. We'll talk about gases too in a second. So the definition for an ionic bond, okay, or at least a workable, usable definition for an ionic bond, is a metal bound to a nonmetal. That's the only one that really is going to work for us to go through and manipulate as far as this class goes. Okay? Unless you want to spend your time to not only understand all the elements on the periodic table, understand the vocabulary, what are the names of each of those, what are their charges, and now memorize their electronegativities. Okay? If you want to do that, by all means, go ahead and do that. Otherwise, you need to memorize this rule. Okay? So I'm telling you, memorize one thing or memorize 118 things. Your choice. Okay? What happens when we move to a covalent bond? Okay, so how did we recognize a covalent bond? Yeah? Heard someone start to say it? So it's a nonmetal bound to a nonmetal. Okay, so we could pick two examples. I'll pick carbon to carbon, and I'll pick hydrogen to oxygen. According to our classification so far, we really only have two types, right? Metal bound to nonmetal ionic, nonmetal to nonmetal covalent. Okay, so that says anything that's an ionic bond should act like an ionic bond. Anything that's a covalent bond should act like a covalent bond. There are only two categories. Okay, is that true? Okay, no. How do we know that? Because it's chemistry, that works. Okay. We know that because when we go into the lab and look at those individual molecules and we say, how does it interact with another molecule? We notice there are drastic differences in those interactions. Okay. If I take a look at, let's switch this bottom one up even further, a hydrogen bound to a carbon versus a hydrogen bound to an oxygen, those interactions are massively different. Okay. A classic example for a hydrogen bound to carbon, we could look at methane, CH4. What do you know about methane? Don't tell me it's stinky. It's not stinky. Flammable. Anybody else know? Are there two M's in flammable? I think there's two M's. What else do you know about methane? Yes, it is a biological decomposition product. When you make it, what phase is it? Okay. What would be our counterexample for the HO bond? For a molecule. If I did methane and I said I just want to look at CH bonds and I picked CH4, what do you think we might expect for an example for HO? Good call. H2O. What can you tell me about H2O? Okay, we got a water. It's liquid. Okay. Non-flammable. Okay, why is that kind of problematic? Well, if we take a look at our systems, we said there's two types of bonds. Everything that's ionic should act ionic. Everything that's covalent should act covalent. But when I take a look at a water molecule to a methane molecule, both of them composed of the exact same bond, do I get the exact same physical observables?
Strength of the bond?
No. Something is different about those bonds. That difference is what we now have to subcategorize. Okay? That comes back to electronegativity. Okay? So we could again figure out the difference between these by memorizing all of the electronegativities. But when we talked about this the first time, what did I say? You don't need to memorize that. We have an alternate method. Okay? How do we know we have a covalent bond? What was the rule I told you? same element, so same bound to same, and carbon bound to hydrogen. That's our rule of thumb. Our strict comparison on this is equal sharing of electrons. Okay, so the complete opposite of the ionic bond. What happens when we move to the polar covalent bond? Okay, so if we now look at our sharing of electron option, ionic said no sharing, covalent is equal sharing, polar covalent is floating somewhere in the middle. Unequal sharing of electrons. Which again takes us back to this silly having to memorize all of the electronegativities. Okay, what was the rule of thumb that I told you to go through for our polar covalent? Everything else. So if you memorize your extremes, the ionic circumstance and the covalent circumstance, what you would go through and do is just say, is it ionic? No. Is it covalent? No. What does that mean? It's polar covalent. Okay? 3 things. Process of elimination, and we can eliminate answers. Okay? This is kind of an odd process for a lot of people to think about. Why? Because to solve the problem, you failed. That's ultimately what you're doing. You're testing and saying it's wrong. Okay? How many of you like to go through an exam and say, oh, it's wrong? Or look at your exam and say, oh, it's marked wrong. And we go, oh, yeah, I got it wrong, yay. Yeah, nobody likes to do that. Why? Because we're trained to think wrong is bad. Wrong is not bad. Wrong allows us to know that that's not the answer. If we figure out what all not the answers are, what are we left with?
Right answer.
The right answer. Okay, so we can use process of elimination to process and deal with our problems. And you have to be thinking about that failed attempt just as much as a successful attempt, because both are valid. Okay? So these 3 classifications you must know. Okay? If I could write another test, I would write another test, because I'm still seeing people miss these 3. Okay? This is ridiculously important. All that other stuff that we throw at you in chemistry, it's kind of boring and meaningless. You just calculate a bunch of numbers and punch stuff into a calculator. Who cares? Okay? What we're concerned about is how 2 atoms, any 2 things, interact with each other. That interaction is what drives chemistry. It's what drives biology. Right? It drives taking of medicines. It drives everything that you could possibly imagine in your life. It comes back to how any 2 things interact with each other and how do we subcategorize those rules. Okay? Chemistry is just providing you another rule set to look at. Okay? So within this, we already started to allude to something else. This describes the bonds. But when we looked at water versus methane, we saw drastically different properties. Okay? That means when I take a whole bunch of water molecules and a whole bunch of methane molecules, I see different things come out of it. Why do I see those different things come out of it? The bond leads to that characteristic, but it's not the explanation of it. What do I mean by that? If I take a look at a bunch of water molecules, I have a bunch of H2O. Okay? And if I'm looking at trying to convert this from a solid to a liquid, what do I have to do? Or let's push it to the extreme, a solid to a gas. What do I have to do? To add heat. What's that heat doing? It's actually not exciting the electrons. Let's go through another picture here. Pictures are fun. I'm going to draw some shapes here real quickly, and you need to tell me what phase I'm in. I didn't even finish drawing. Let me finish drawing. Yeah, man, jump the gun. Okay, what phase do we have? How do you know it's a solid? We're looking at an extreme organization. All of those are neatly packed next to each other. Okay? Okay? New drawing. It's supposed to be the same objects. What phase do I have now?
Gas.
How do you know it's a gas? They're spread apart from each other. Okay, you'll notice we don't have that same nice organized lateral structure. So for me to transition from the solid to the gas, what do I have to do? I already suggested one thing, so let me get rid of that option now. We added heat. What did that heat do to the molecule? Okay, here's where we got to be careful with our approach. If we break the bonds, do we have the compound anymore? No. What we did was we took the squares and we broke them up into triangles. That's breaking the bond. Okay, those squares are held together by bonds. So what are we breaking then if we go into the gas phase, if we're not breaking the bonds? There's got to be something else there. Okay? At least in the U.S., with our U.S. culture, our marriage cultural system, how often do we go from single to married? You just wake up one day, whoop, you're married. Does that happen very often?
Seems like it's
Doesn't happen all that often. Why not? Would you like to wake up one day, oh, geez, who's this person next to me? I'm not married to him. How did that happen?
attraction.
Okay. There's some kind of attraction that we, and at least in our culture, tend to build. We go out and find somebody that we're attracted to. We date them. Okay, we get close to them. We start to understand them a little bit more. And we say, no way in hell I'm living with you. And we break up and find somebody else. Okay, and we keep going through that process until we find something that works. Then we can form that bond, okay, that marriage aspect. But we had this searching process of starting to almost test out the marriage. That's what our dating process is. We're testing out the marriage. Hey, how are we going to be as a married couple? Oh, we're horrible? Yeah, never mind. Okay. What's that intermediate stage? Well, in our relationships, that's dating. What's that intermediate stage when we look at molecules? Okay. Kind of a harder process because we haven't talked about it. What we're looking at is an attractive force between those molecules. So all we've discussed so far are these bonds between those molecules. But guess what? We also have some stuff in between each of those. And when we look at the solid phase, how many of those interactions do we have? What do you think? A lot or a little? A lot. That's why it's being held together as a solid. When we jump up to the gas phase, what happens to those interactions? They are effectively gone. Right? Think about the approximations we made when we looked at a gas. We said particles held no volume. Right? And they were not attracted to each other. Okay? And what did our gas particles do? They filled up the volume as much as they could. Why are they filling up the volume? Because they're trying to get away from every other particle. Okay? We've negated all interactions when we've moved up to the gas phase. So what about those interactions changes when we change the bond? Right? Because when we looked at methane with just a covalent bond or a nonpolar covalent bond, we're start in the gas phase. But if we look at water, H2O, we start in the liquid phase. So something about our bond is changing the interactions between each of those particles. Add another layer onto this, the ionic bond. What phase do we start out with an ionic bond? Classic example of an ionic bond. Sodium chloride, also known as salt. What phase does salt start as? Solid. Okay. Why, when I change the bond, I'm changing those elements, do I all of a sudden see a change in phase? Something about the interaction between those two elements is now affecting how that molecule interacts with another molecule. That secondary interaction is what's allowing us to see the physical properties that we associate with individual molecules. Okay? So now that's what we want to look at. Okay, so we've got a whole bunch of things up here. These are into quadrants. So we can kind of quadrant this thing off. What we're looking at is an individual molecule on the left, and I want to see how it interacts with the same type of molecule on the right. And because we only have two atoms, we've got only two possible ways that it can interact. So if we take a look at that top situation, sodium bound to chloride, there are two ways that that molecule can interact with another molecule. Which method is the preferable one, the top one or the bottom one? Everybody agree already with him? He could be wrong. I actually didn't look at the answer. All right, you all agree with him? Is that a no?
Are you talking about the
So we're looking at
NaCl or the ClNA?
the NaCl or the ClNA. It said which of those two interactions is preferential? The top interaction or the bottom interaction?
Same. The top, no.
Okay, now we're getting some more. I think you're just saying it again louder and trying to hide your voice. That didn't count. Okay. How would we be able to predict this? We can look at the balance of charge within our ionic bond. Okay, whoops, gave that answer away. We could look at the balance of charge within our bond. Where are the electrons in that bond associated? Okay. So what type of bond is it first? We have an ionic bond. So what happens in an ionic bond? Where do those electrons exist? Got to be careful. What was our definition for an ionic bond? They are transferred, which means are the electrons existing between those atoms? No. They're being transferred to one atom or the other. Which atom picks up those electrons? Okay. So what we're saying is which atom takes the electrons away from the bond? So if it takes the electrons, it holds the electrons. What charge should it become?
Negative.
Negative. It's now gained electrons. Okay. Which atom would preferentially take bonding electrons? Okay. I wanted the definition. What was your statement? The most electronegative atom should take the electrons. Okay. So instead of jumping straight to the answer, sodium or chlorine, let's come up with each of the steps. Our step is that we need to know the most electronegative atom. Okay. Now we run into an issue. What's that issue? You have to know which one's the most electronegative. How can you know that? You could have gone through and memorized all the electronegativities, or you did the other option, which I told you to watch out for, is look at the trends. What's our trend for electronegativity on our periodic table? Low on the left, high on the right. Fluorine is our most electronegative element. Our least, the complete opposite side of the periodic table and down. Okay? So if we now then compare sodium to chlorine, where are they on the periodic table? Sodium's on the way left, which already suggests not very electronegative, because fluorine was our most. Where's chlorine? Right underneath fluorine. So if fluorine's our most electronegative, which one's closer to fluorine? Chlorine. Which means chlorine is more electronegative. The more electronegative an element is, that means the more likely it will take the electrons. So if we now want to add a layer of organic chemistry into this, what we can do is use curved arrows. Okay, what these curved arrows are going to represent is I'm going to start my arrow where the electrons are. Well, where do the electrons start? In the bond between those two atoms. That's what we've got drawn. So that's where our electrons started. Where did they go to? To the chlorine. How many electrons were in that bond? How many electrons are in every bond? 2. So I'm going to show that I have moved 2 electrons from the bond to chlorine with my arrow. Any guesses how I could do that? Really subtle. Now I've shown it. How do I show only 1 electron's moved? Turn it into a fishhook arrow. There's only 1 arrowhead. Now I'd say only 1 electron moved. If I want to show 2 electrons move, double-headed arrow. Ta-da! Chlorine started neutral. It just gained an electron. What charge is it going to become? Negative. What happened to the sodium? Lost an electron, so it is now positive. Okay, this balance of positive and negative, is that going to hold true for every molecule of sodium chloride? Yes. So what can I do now with my other molecules? Put the positive and negatives associated with the right atoms. Okay, well, the positive was on the left-hand side of the equation, or my molecule. The negative was on the right-hand side, so I'll just go through and repeat that over here. Is that right? No. Why did we decide where the positive and negative were? Where the electrons went, based on the electronegativities. So that bottom case is not true because the chlorine is now swapped. How does this help us decide which interaction is favorable? Opposites attract. Okay, if we had like charges, they repel each other. Remember what happens when you get 2 electrons near each other? Freak out and run away from each other. Okay, why do we have neutrons in our nucleus? To hold the protons together, because the protons get near each other and do what? Repel away from each other. Okay, so like charges repel, which means that bottom interaction is horrible. Top interaction wins. Okay? What happens when we move to the next one down? Why not? We'll start with this one. Which interaction is favored? Okay, only 2 people are participating, which makes this a little bit more difficult. I heard a top and I heard a bottom one.
I said the bottom one.
Ooh, we got a top switching to the bottom.
I think the bottom one because hydrogen is more electronegative than chlorine.
Now you're all agreeing it's the bottom? Really? You guys all want to say it's the bottom one?
Hydrogen's always, oh wait, no, it's not.
This one's pretty hard. I'm not going to lie.
Top.
Okay? It's hard, so let's pause for a moment. Step away from that one. Let's try the upper right-hand quadrant. Which interaction is favored, top or bottom? Okay. How do we figure out which interaction was favored in our sodium chloride example? We had to look for our charges. What was happening with our electronegativity? So let's do the same thing here. Let's take a look at that OH bond. Where do those electrons in that OH bond spend most of their time? The general answer would be oxygen's a specific answer. The more electronegative element. Which element is more electronegative? Oxygen or hydrogen? Oxygen. Which means if we try to draw our arrow again, our electrons come from the bond and they spend their time primarily with oxygen. How many electrons did I move over? 2. Okay, so we're pushing this to the extreme. What charge does the oxygen become? What charge does the hydrogen become? Is this same interaction going to hold true for each molecule of OH?
Yes.
Yes. Which interaction is favored? Top one's favored. We're balancing out those charges. Okay, before we hit that lower left-hand corner, I'm going to add one more layer of information into this. Sodium chloride had what bond? OH had what bond? What made it polar covalent? So it was a covalent bond, two nonmetals, and it's not same to same or carbon to hydrogen. So that means it's polar covalent. And in a polar covalent situation, the electrons are shared unequally, which is why we can see this charge build. Okay, with all that information, last example. First question I'll ask, what type of bond? It's a covalent bond because we have a carbon bound to hydrogen. I'm going to give you 2 minutes. Talk with the people around you. Decide which interaction you think is favored. Yes, this involves talking. Walk through the process that we just went through and did. And it's not, I think it's top. It's, this is why it is the top. Top or bottom? Everybody said the top. Not 5 minutes ago, you all said it was the bottom. Why are you all switching up to the top now? Because you said top to begin with. Okay, so let's take a show of hands. Does everybody agree with Nick? Said the top. Who agrees that it's the top? Who thinks it's the bottom? Who thinks this is a trick question? It's both. Why is it both? There's no charge. The electrons are shared equally between the carbon and the hydrogen. There is no difference in the electronegativity. Which means, where do those electrons spend their time? Equally on the carbon, equally on the hydrogen. Well, what charge is the carbon?
0.
0. What charge is the hydrogen?
0.
Is this interaction going to hold true for all bonds of carbon and hydrogen? Yes. So we now go to our other molecules and we line those up. Is there a favorite? No. Everything is 0 to 0. There is no favorite. Okay? So both interactions are equally likely to happen. Kind of a tricky concept. Can we push this a little bit further? Of course, why not? Which of these interactions is the strongest? We got 3 interactions shown. Which of those is the strongest interaction? Okay. So to be clear, where's our interaction? What color is it in this? Color's a bad choice. Is it our solid line or is it our dotted lines? At this point, we're just trying to figure it out, see what you guys come up with. There's no right or wrong. Where's our interaction that we're talking about? Is it the solid line between the atoms, or is it our dashed line? Where's our interaction? It's the dashed lines. Okay. Are any of those dashed lines covalent, ionic, or polar covalent? No. For it to be those, it has to be a bond. To be a bond, what does it have to be shown as? A solid line. Okay? So our answer cannot be well, the name of our interaction cannot be ionic, polar covalent, or covalent. Okay? Which interaction? I'll number them so that we don't use that same terminology. We got 1, 2, and 3. Anybody having a hard time deciding the strongest? Why? Why? There's the example I wanted to hear. Why do you say the covalent would be the weakest? I don't like your term.
No, it's because it's not actually
Hydrogen
charged.
bonding doesn't come into this at all. We haven't even talked about that.
There's no potential charge.
There's no charges. So when we look at case 3, there is no charge between those molecules. We would expect the weakest interaction there. Why? There's nothing to neutralize. Why would those molecules reach out to interact with another molecule if it's already happy? If it's already neutral, it says, F this, I'm happy. I'm not going to talk to anybody else. All right? Our strongest becomes much more challenging. Because when we look at case 1 and 2, what did we add atop all of our drawings? Charges, positive and negative, both cases. So those two are hard to tell apart. Covalent, all of it's 0. That one's at least different. Okay? And you said it's the weakest because there's neutral charges. There's nothing to cancel out, so there's no reason for that molecule in 3 to try and do any kind of interaction. So we would expect that one to be the absolute weakest interaction. Is everybody okay with that?
Okay, so are we talking about molecules interacting with other molecules?
That's all we're talking about. But what we've done in this case is most molecules have a lot more atoms, so we simplified it down to just a single bond for our
I'm
molecule.
talking about the way the strongest bond between atoms. You're talking about
Nope. We're talking about the interaction between separate molecules. Okay? So let's move up to our 1 versus our 2. I showed positives and negatives all the way through those, right? We've talked about this before. I've tested you on it at least 3 times. Okay? And in those 3 times, most people got this wrong. Okay? So let's go back and look at this. Can I actually say, in the polar covalent situation, that that oxygen is actually negatively charged? Okay, and Brian, you started to allude to this, which might be where you were going with it potentially when you said this earlier. Can I say that oxygen is negative and that hydrogen is positive, just as much as the sodium is positive and the chloride is negative? Why can I not make that comparison?
Different charges.
It's getting towards the partial idea. Why is it partial and not these formal, full-on positives and negatives? It's the amount of sharing of electrons. In an ionic bond, are you sharing electrons? No, it is a complete and full transfer of electrons. In the polar covalent bond, what's happening with the electrons? There is some sharing. So it's not a complete transfer of the electrons. It's only a partial sharing of electrons. Which means while that oxygen is becoming negative, I cannot show it as a full negative. I can only show it as a partial negative. And that comes back to the bond characteristic. It's a polar covalent bond. Okay? So how do I show in my drawing that that's not a full negative? Okay, let's do it this way. You all have pens and pencils, right? Every time you look at a polar covalent bond, when you're asked the charges on it, you need to write out partial negative and partial positive, partial negative, partial positive. You ever write a word so much that it actually stops looking like a word? Partial. This is getting really tedious, isn't it? There's got to be a better way to write that out. What's that better way? We invented a symbol. We used a symbol. What was that symbol? Our delta symbol. That shortens the amount of work that we have to go through and do when we write these out so that we understand that it's not full negative, it's not full positive. What does that mean about the interaction? Which interaction would I predict to be stronger? Where I'm canceling out full charges or partial charges? Full charges. Those are the most incredibly unstable. Remember, all charge is bad. You don't stick your finger in the electrical outlet because what's coming out of the electrical outlet? Charge. Okay? So charge is always trying to get neutralized. It's all chemistry's ever trying to do. As chemists, what do? We stick something in the way so that while it's neutralizing, it does something for us. That's what chemists do. Okay? You look at a battery. What's happening in a battery? You're getting a chemical reaction in the battery where electrons are being transferred. But us as chemists and engineers went in and said, wait, chemicals, I'm separating you. The only way you can react with each other is if you go through this fancy little wire. And in the process of going through that little wire, what happens? It then powers something that we want. Okay? Same thing is happening with our molecules. Everything is trying to neutralize. If I have really big charges, those really big charges are ridiculously unstable and need to neutralize as fast as possible. So if we have a massively negative structure and a massively positive structure, when we put those two together, what happens? We get a massive release of energy that's really not happy. Okay? Well, for us, if we've controlled it, that's pretty nice. Okay? If we have very small charges, we get a relatively weaker release of energy. How does this translate into what we would then visualize? Well, in CH4, our example for our covalent bond, what phase did we have? It was a gas. Why? We have the weakest interaction between those molecules in CH4 because they're already neutral. They don't want to interact with each other. Okay, well, if we make them a solid, they have to interact. What happens when we moved up to our polar covalent? We had to use water. What happens to our phase in water? Now it becomes a liquid. Why? Because if I put it into the gas phase, I'm neutralizing water's ability to be able to neutralize its own charge. So it starts to panic. Okay, it says, you got to give me a lot more energy to break that interaction. So at room temperature, we get a liquid. What happens when we move to our salt, our sodium chloride? When we look at its phase, what happens? It's a solid. Because to break the interaction, to get those molecules away from other molecules, we have to add in a lot of energy to break that interaction, to spread them apart. What does that turn into for us? How do we measure the amount of energy it takes to take a liquid to a gas? What's that process known as? Liquid to a gas. Look at evaporation if it did it on its own. We force it to happen, we call it something else. Boiling. The point at which that happens is the boiling point. If I look at the boiling point for water, based on this intermolecular attraction, what would I expect the boiling point of water to be? Relatively high or low? Okay, let's, I guess, pick a different situation. Water in comparison to sodium chloride, which one would I expect to have the higher boiling point? Sodium chloride, because stronger intermolecular forces. Okay? And you'll notice that what I'm saying here is interactions, or intermolecular forces, not the bond. The bond is something else entirely. When we change phases, we are not breaking bonds. We are breaking forces. Okay? It's the interaction between molecules. Okay? So what we can go through and do is then subcategorize things into these individual types of forces. Okay? So in our upper left-hand corner, we had the ionic bond. Well, what force do we end up calling a molecule that has ionic bonds? What's our purple interaction now? What do we end up calling that? Electrostatic. Or, very unfortunately, we call it ionic. Okay? Yeah, I didn't invent it either. Okay? So we can look at an ionic bond generating an ionic force. An ionic bond in the drawing that I've got shown here is what color? It's the red one. And our ionic force is our purple one. Right? You're looking at interactions at different states. How did we get an ionic or electrostatic force? Well, what did our molecule, what type of bond did we need to have? We needed an ionic bond. Well, let's change that around. Let's call this our bond needed to be ionic. The carbon-hydrogen situation was our weakest force. Our absolute weakest. Okay? That interaction was so weak, okay, and this is where we run into issues with naming. It was such a weak interaction that what did we assume from the get-go? It's so weak, it is irrelevant. Turns out, is it irrelevant? No, it does actually carry some weight. Okay, so what do we end up naming that interaction? Not the irrelevant force, but we name it for the person that discovered and said, hey, you can't ignore that force. That person happened to be? Nope. It's a subtle patterning in how I set up these slides. Van der Waals. And I think Van der Waals was in London when he discovered the force. I actually don't know that. Okay? So our weakest force, just right up here, this is our strongest force. Our weakest force is in the Van der Waals. When did we get the weakest force? What type of bond structure did I need? I needed a covalent bond. So if I know something about my molecule, the type of bond structure, I can then predict its forces and how it's going to interact with its outside environment. When we looked at the OH bond, okay, that was a stronger force than the London dispersion, but weaker than the electrostatic, than our ionic. So it's got to be somewhere in the middle. Any guesses? All right, we can draw it up again. No subtle hints here or anything like that. Draw it in the middle here. And if we added our charges, we had a partial negative, partial positive, partial negative, and our partial positive. I'm going to pretend I can do this. If we cover that up, I see y'all got to look this direction, by the way. Okay. We've got the OH. Does it have a pole? So like the planet has a pole, right? North and a south pole. Does a magnet have a pole? Yeah, north. Oh, that was a dumb example, but north and a south pole on our magnet. Okay. Does this molecule have a pole? What are those poles? How many poles do we have? 2. So we could call it 2-pole. That's kind of boring. Come on with another name. Why dipole? Di means 2. So that molecule has a dipole. So I'll refer to that molecule from now on as dipole, because I'm creative. Does this molecule have a pole? Yeah, how many poles does it have? So what do we want to call it? Dipole. What's the interaction between dipole and dipole? It's a dipole-dipole force. Super creative. Right, so the interaction that we get from a dipole, okay, comes from what type of bond? A polar covalent bond. So if we just break down our 3 bonds, we get 3 forces. That actually kind of makes sense. 3 bonds, 3 forces. 1 for each. Except, do I just have 3 forces listed here? No, I added an extra one. What's that extra one? Hydrogen bonding. You'll notice the bonding is in quotes. Why? because it's not a bond. Where is it relative to the rest of the forces? What? It's closest to the weakest? Oh, it's pretty close to our strongest. Remember, I said I organized this with some sort of logic to it. I mean, I never understand my logic, but it's at least there. Okay. So it is a relatively strong force. Why might we separate it out as its own separate force? Because it is that strong. It's stronger than a dipole-dipole, but it's weaker than an ionic bond. Or, sorry, an ionic force. Right, well, when might I see hydrogen bonding? What do you think has to be present to have hydrogen bonding? Hydrogen's a good guess. Okay. Hydrogen, if we look at our periodic table, is way freaking far away from fluorine, which means not very electronegative. So it's effectively a metal, but it's not a metal. How do we know it's not a metal? Because it's red. Okay, which means it's a gas, and no metal is a gas. Okay, so it's a nonmetal. What could I bind it to get a really large difference in electronegativity, or what could I bind it to get a really large partial charge buildup? Because I'm trying to get as close to an ionic bond as possible. What could I possibly bind the hydrogen to get a massive difference? What characteristic is necessary about that element? It has to be not negative necessarily. I think someone just mouthed over the front word on that. It has to be highly electronegative. So what elements are highly electronegative? Fluorine. So if I have a hydrogen bound to fluorine, I can do hydrogen bonding. Okay. What other elements are highly electronegative? Oxygen and nitrogen. To have hydrogen bonding, I have to have a hydrogen physically bound, solid line, to fluorine, oxygen, or nitrogen, or phone. Hydrogen bonding is phone. No? Okay. Like fun, but phone. Is this thing on? We have to have that presence. If it is there, I can have hydrogen bonding. To generate that hydrogen bonding, though, we have to have that system, right? Well, what is generated if I bind a hydrogen to an oxygen? Look at our case. What did I build? I built partial charges. How many partial charges on my molecule? 2. Are those partial charges different? Yes. So if I name this section here, what can I call it? A 2-pole. Dipole. To have hydrogen bonding, what do I need? Dipole. Dipole. I must have a dipole-dipole force before I can even evaluate if I have hydrogen bonding. So to have hydrogen bonding, you must see a dipole-dipole. Then you can evaluate your structure. Is there a hydrogen bound to fluorine, oxygen, or nitrogen? If that condition is also true, you now have hydrogen bonding. Okay? Why does this help us out? Let's take a look at some new molecules here. Actually, I think I'm going to advance. Yeah. A couple new molecules. We've got HOH. And let's take a look at COC. Can we make some predictions about those two compounds? Which one would I expect to have the lower boiling point? What determines the boiling point? Sort of. Not quite jumping to bond, the strength of the force. The stronger the force, the higher our boiling point. Okay, but how do we determine the force? By looking at the bond. Okay. The more polar the bond, the stronger the force. Which of those two molecules is going to generate the strongest force? Well, we'll go back and look at the bonds. What kind of bond do I have between H and O? Bond. I have a polar covalent bond. What does that mean for the force? It's a dipole-dipole force. If I have a dipole-dipole force, what should I do next? See if I have a hydrogen bound to oxygen, nitrogen, or fluorine. Do I have that? Yes. So what's the force that I've got coming out of this molecule? Hydrogen bonding. Is that the strongest force? No, we got ionic hydrogen, so we can't do any predictions yet. We've got to look at the next one. What type of bond do I have between oxygen and carbon? Right, oxygen and carbon are both both non-metals, which means covalent type. Is it polar covalent or non-polar covalent? What was our rule to separate those? Covalent was same bound to same and carbon to hydrogen. Is oxygen the same element as carbon? No. So is it non-polar covalent? No. That makes it polar covalent. What does that mean as far as our force then? It is dipole-dipole. Once we find a dipole-dipole, what should we do? See if we have hydrogen bonding. Do I have a hydrogen bound to oxygen, nitrogen, or fluorine? No. So what force do I have for my COC? Dipole-dipole. Which force is the weakest? Dipole-dipole. What does that mean about the interaction between that molecule and another molecule? Is it weaker or stronger? It's weaker. Which means what about its boiling point? It's lower. So understanding something about electronegativity, okay, and our bonds, we can then predict that the compound COC is going to have a lower boiling point than water. Which is true. It does. Good job. So a basic understanding gets us to a physical observable, a comparative physical observable, but it's still a physical observable. That's pretty awesome. Okay? That can help us out with phase transitions. That can also help us out with vapor pressures. Okay? Vapor pressures was our compound wanting to become a gas. What would we expect would be our force for a compound that wants to become a gas? We expect a weak force or a strong force? A weak force, which means what type of bond? Covalent bond. Okay? So manipulating our bonds and forces based off of what we understand for these terms can really help us predict and ultimately rank molecules relative to each other. Ranking questions seem to be the hardest for students to figure out. If I give you 3 things to rank, how do you go through and approach that problem? What does systematically mean? I completely agree with you. So knowing the rules help. What's that? Pick any 2. Does it matter what 2? No. Pick 2, compare them. Get them into a rank system first. Then what do? Add 1 more. And you're going to compare that 1 more to what? One of the 2 you just compared. So at any point during a ranking question, how many elements or how many things are you comparing to each other? Only 2. Never more than 2. Don't skip steps. Okay? Last thing, phase transitions are important. So that's our melting points and boiling points. We just came up with a way to interpret that. The other big one here is solubility. All right, what's happening? Actually, it's on the next little section. So before we even do that, let's take a look at what this figure means. We've got bonds on the left, forces on, left and right. Okay? As we move up on the right-hand side, what happens to the strength of the force? It increases. So it gets stronger as we go vertically on the forces. Does it get stronger when we go to bonds? This is where it gets tricky. There is no assumption of bond strength. Okay? And in fact, if we look at bond strength, which bond is actually stronger? Our covalent bond is stronger. Why? You're sharing electrons. Sharing of electrons makes it very difficult to rip those atoms apart from each other. Whereas in the case of ionic, they aren't sharing electrons. So what does that mean about the bond? Well, the bond's not there if you aren't sharing electrons, so how easy is it going to be to rip two molecules that aren't bound to each other away from each other? That's not too bad. Okay? So, what do we do with our forces and our bonds? If you find out you have a covalent bond, let's say it's blue. What color is your force? Blue. If you have a polar covalent bond, what type of force do you have? Dipole-dipole. Okay? This figure is set up to reveal a lot of the interactions between, or the relationship between bonds and forces. And it is a full spectrum. That's what makes it even more challenging. Just like our relationships, we go from being completely single to now maybe talking to someone, to now maybe hanging out with friends, I don't know, to now maybe dating, to now saying, I don't like you, so we go back, to now maybe dating, to now dating seriously, to now getting engaged, to now getting married, now getting divorced, now getting married. Okay? We've got all of these individual steps within it. It's a complete spectrum. We don't just jump from one end to the other. Okay? Same thing's happening with our interactions. At our London dispersion interaction, that is our weakest interaction. What happens as we continue up and around this circle? What happens to the strength of our interaction? It gets stronger. Okay? What happens as our interaction continues to turn around the circle? It gets stronger still. Remember, you're sharing electrons. Okay? And that's one of the confusing things with this approach. Everybody goes, well, an ionic compound's got to have a really strong bond because it's a solid. When we talk about solids, liquids, and gases, are we looking at the bonds?
No.
We're looking at the forces. And for an ionic compound, that has a really strong force. It should be a solid. For a covalent compound, everybody goes, oh, a covalent compound has a low boiling point. Methane. So that's got to be a weak bond. No, it has a weak force. Okay, so our melting points, boiling points, all of those physical observables are ultimately based on the forces. We can determine the forces from the bonds. But as we continue to move around that, we're ultimately looking at London dispersion, where there's absolutely no sharing of electrons, to now starting to move to, hey, you have some electrons. That's kind of cool. I'm going to get a little bit closer to you. So, hey, you really got some electrons. I think I'm going to actually start taking those electrons from you. Okay? To now, maybe we can start sharing again. I'll start sharing. We can cohabitate and actually have an equal sharing of those electrons. Okay? So it's a smooth transition all the way around that we have subdivided into these individual categories. But these individual categories determine all of the physical observables that we could ever possibly see. Right? Really, really cool. So I appreciate the yawning. It makes me feel good. Okay? So, solubility. Okay? What's happening with solubility? Okay, well, the term solubility is just looking at something dissolving in something else. Okay, so we want to come up with a rule of thumb that allows us to approach this. Okay, that rule of thumb is like forces dissolve like forces. So if you look at a compound that is ionic, what compound would you expect that ionic compound to dissolve in? Probably one that has a similar force. One that would have similar force would be ionic. Okay, so if we look at two examples here, water's the same case for both of these. We're looking at the compound ethanol and the compound propane. What do you know about ethanol? You know nothing about ethanol, right? Because you're not 21? ethanol, alcohol, vodka, all that fun stuff. Okay, that's what you ingest, is that. What you don't ingest, that's 21. Okay. What do you know about the solubility of that compound in water? Yeah, some of you are over 21. What do you know about the solubility of that compound in water? Very, very, very soluble. Okay. Next time you've got your vodka and you want to dilute it a little bit, add some ice to it. What happens? Do you see two layers form? No, the ice melts, and what happens? You see one solution. It's because the water and the ethanol dissolve with each other. Why did they dissolve? What's the strongest force that water puts out? How do you know it's hydrogen bonding? It's a polar covalent bond that generates a dipole-dipole force. Do we have a hydrogen bound to oxygen, nitrogen, or fluorine? Yes, we've got hydrogen bonding. We now look at CH3, CH2, OH. There's a lot more bonds in that one. This makes it a little bit trickier. So what do we technically have to do for this one? Look at every single one of those bonds and evaluate them. Right? And decide what's the force, the strongest force that comes out of that. When we look at CH3s, all of those bonds are nonpolar covalent, which generates London dispersion forces. What type of bond do we have out on the end? We have a polar covalent bond, which gets us to dipole-dipole, which gets us to hydrogen bonding. Is hydrogen bonding similar to hydrogen bonding? Yeah? What does that mean? Soluble. They mix. What happens when we look at water and, say, propane? Water had our hydrogen bonding. What does propane have? We have a nonpolar covalent bond, which gets us to London dispersion forces. That's our strongest force that we can pull out of this. Oh, that's kind of boring. What's the similarity between hydrogen bonding and London dispersion? Virtually none. So what happens with the solubility? Insoluble. Those two don't mix. Okay? So looking at our forces allows us to be able to predict these things. And it is massively cool. Okay? If we jump up to ionic compounds, those get a little bit trickier. NaCl is what? Salt. Is salt soluble in water? Yes, that's a bit odd. Why is that odd? What force does salt have? Ionic. What force does water have? Hydrogen bonding. Those are close to each other, but they aren't one and the same. Okay? Why do salts end up dissolving in water? It has to do with one of the properties of water. When we look at an individual salt molecule, when it hits water, it dissociates into ions, Na plus and Cl minus. For us to dissolve, we have to break the force between those. Okay, well, that's a really strong force between sodium and chloride. And if I look at the interaction between a water molecule and that, which of those interactions is stronger? Red or blue? Red. I'm fully neutralizing both of those charges. So why does salt dissolve in water? How many water molecules end up associating with that sodium? Just one? You're looking at another one over here. And another one. And another one. So the sum total of all of the hydrogen bonding ion interactions that come into adding that into water outweighs the ionic interaction. Okay, so almost all of our ionic compounds are soluble in water. Are there exceptions? Absolutely. Where do you find those exceptions? In your solubility rules. Okay? So, water's cool because of all these intermolecular forces that can come out of it and can dissolve multiple different things. To decide whether it can dissolve it, what do you have to look at? Our forces. To figure out our forces, where do we have to look? Our bonds. How do we know what bonds we have? We have to have some of those rules memorized. How do you know you have an ionic bond? Metal and a nonmetal. How do you know you have a nonpolar covalent bond? Nonmetal, nonmetal, and same to same or carbon to hydrogen. So our difference in electronegativity is very small. You have to know those to do these kinds of problems. If you do not know those, you will not be able to answer any ranking question when it comes to individual structures. Okay? Super, super, super important. Questions? Was today really that boring?
I'm just really tired.
I'm just going to bring up a quick concept just because we got a couple minutes here. Those of you in Tuesday lab already heard about this. Those of you in today's lab will talk about it again a little bit more. Okay? When we look at an individual solution, we dissolve our compounds into water. So if I now take that solution and react it with another solution, we now have a problem. Am I reacting just aluminum bromide with silver nitrate? Why not? How do you know that? We have AQ. What does AQ mean? Aqueous. There's water present. So if I just measure the volume of that solution, am I measuring just aluminum bromide? No, I'm measuring water too. Okay, so I can't measure the volume. Well, maybe I weigh it out. Can I figure it out then? Well, the weight is going to be aluminum bromide and water as well. I can't separate the water out of that solution to allow it for me to figure out how to use my balanced equation. So we need to know some more information about this. How do we quantify the silver bromide that's produced in this? Okay, or how do we even quantify how much aluminum bromide we started with? Okay, this comes back to this concept of concentration. When we're looking at concentration, we're looking at how much of an individual species is dissolved in a solvent. Okay? In this case, our solvent is water, and our species, also known as a solute, is our aluminum bromide or our silver nitrate or any of those that are aqueous. So we need to see a relationship between those. Some kind of amount to a volume. We need that conversion factor. That conversion factor would be provided to you. The standard way to provide this information is with what unit? Molarity, which is the symbol capital M. Okay? Horrible, horrible unit, because where have you seen capital M before? Nowhere. It's completely useless. So if you see capital M, what you need to immediately convert that into is moles over liters, because that's what molarity means. Moles are a measurement of what? An amount. Liters are a measurement of volume. It's a new conversion factor. That's all it is. You'll be provided that information or asked to solve for it. Either way, it's an amount per volume. We'll pick up there on whatever it is next week.